Hello, my name is Tim Dawson, Senior Research Engineer at CFD Research Corporation, and today I'd like to tell you about a flamelet-based approach for spray combustion simulations, which we have developed in collaboration with Stanford University. Before I get into the main topic of this presentation, I'd like to share a little bit about CFD Research. Just like it says on the tin, CFD Research specializes in the development and application of cutting-edge multi-physics simulation software. We can simulate detailed combustion, fluid structure interactions, ballistics, hypersonics, detonations, cavitation, plume signatures, plume surface interactions, and more, and that's just within the Aerospace and Defense Division. We also boast multiple laboratories for bioengineering, energy storage research, and propulsion test facilities. Our main office is located in Huntsville, Alabama, in close proximity to NASA Marshall, the Redstone Arsenal, and many prime contractors. Our staff is highly qualified, most with advanced degrees and many with secret or top secret clearances. Moving on to the present work, the motivation for this STTR project was a need to model liquid fuel spray in turbulent combustion under PMA 265. Such a model must be physically accurate, computationally efficient, and encapsulated in a software API for coupling to reacting flow solvers. These simulations would be used to support the design and performance predictions of naval propulsion systems such as gas turbine engines and augmentors. Such applications involve complex interactions between the liquid fuel spray and the gas phase turbulent combustion, which can be prohibitively expensive to simulate. Current finite-rate chemistry-based approaches are ill-suited to the task, as detailed models for realistic aviation fuels typically contain hundreds of species and thousands of reactions, making them computationally intractable. Our approach is based upon the flamelet method, wherein the flame structure and effects of turbulence on the chemistry is pre-computed, making it very efficient. Such methods have historically had limited application to spray combustion problems and did not account for some of the key physics we are incorporating. We began with a standard gas phase flamelet progress variable approach, which builds a lookup table for the species from one-dimensional opposed flow diffusion flame simulations. The table is parameterized by the mean and variance of the mixture fraction, which are used to model the effect of turbulent mixing, as well as a user-defined progress variable. Next, the tables were modified to use multi-phase flamelets solved through an Eulerian approach, which could then be coupled to Eulerian or Lagrangian spray combustion CFD solvers. A standalone flamelet library generation tool was created to facilitate this work, handling both gas and multi-phase flamelets with a modified version of the open-source Cantera library. Significant focus was given to the effects of multi-component evaporation and polydispersed spray, as well as low-temperature chemistry, which was found to have a large impact on the flame structure. To date, the gas phase capabilities were demonstrated in both RANS and LES modes using a pressure-based open foam solver and the density-based Loci CHEM solver. Two-dimensional DNS of spray diffusion flames were used to develop and verify the one-dimensional multi-phase solver, which could then be used to generate flamelets which directly encode the effects of multi-component evaporation. The Lagrangian spray module in Loci CHEM was then coupled to the flamelet method through the evaporation source terms, and this has been recently demonstrated on the Sydney Piloted Acetone Spray Flame ACF3 using RANS and LES. We are currently pursuing the Phase 2 option where we intend to demonstrate the solver with large hydrocarbon fuels at transcritical and supercritical pressures. We will also couple the API to a commercial solver, StarCCM+, and perform cross-code validation. At the time of this recording, both gas phase and multi-phase capabilities have been demonstrated with the Flamelet Library Generation tool and the API coupled to the Loci CHEM solver. The Flamelet Solver API provides routines for efficient flamelet table lookup, source and flux term computations, and models for both diffusion and turbulence. Turbulence models available include algebraic and transported mixture fraction variants, formulated for both RANS and LES. The figure on the left here shows a slice of a gas phase flamelet library, specifically for the Sandia Flame D test case. Increasing line transparency represents increasing mixture fraction variance, showing the approach toward a pure mixing solution at high levels of turbulence. The figure on the right shows a planar jet flame used as a test case, comparing finite rate chemistry and flamelet progress variable approaches. Using the flamelet-based approach, we saw a 20 times speedup over finite rate chemistry for methane air combustion, and this gap grows rapidly with mechanism size. This is attributable to the relaxed system stiffness as compared to finite rate chemistry, allowing for larger stable time steps, and the low cost per time step of the table lookup relative to Arrhenius rate computations. The Flamelet library generator is quite user-friendly and hands-off, up to and including the ability to generate a table from scratch with a single command, including automatic selection of an optimal progress variable definition. Expert users can, of course, do far more with it. The current Loci CHEM implementation really serves as the gold standard due to its fully coupled, density-based, and highly scalable nature, and it should be noted that the solver itself is DoD open source. The API, of course, is invaluable for those who wish to enhance their own in-house solvers, and we aim to make this as painless as possible. Finally, thorough validation against experimental data is essential. We have currently exercised the approach on canonical gas phase and spray flames, and are now targeting laboratory-scale combustors with large hydrocarbon aviation fuels. In addition to the software product itself, we offer our expertise in applying it to problems of interest, as well as for developing additional capabilities or integrating it into an established workflow. The final report for the Phase 2 base period is actually due next week, and we are pursuing the Phase 2 option. As part of this, we are seeking industry partners who are looking to enhance and accelerate their spray combustion simulation capabilities, and to provide feedback we can use to further enhance this software. With little to no modification, the approach can be applied to basically any non-premixed spray combustion application. In fact, part of the Phase 2 option will be focused on expanding the range of applicability to mixed mode and supercritical combustion. On this slide you may find contact information for myself, as well as for Dr. Ranjan Mehta, Director of Space Technology R&D and PI for this project, and Dr. Vincent Herrand, Vice President of Technology Commercialization. Please feel free to reach out to Ranjan and myself with any technical questions regarding this work, and to Vincent for any broader business inquiries. Thank you for your time. I would be happy to take any questions or comments, either through our virtual booth or via email.